No, he's right, but they don't have sharp enough or deep enough fangs to actually penetrate human skin typically. Yeah, you'd have to be really, you'd have to really try at it. They're not. I don't think they kill anybody. Yeah, I mean there are super venomous, but I don't think they. Really? But that's what I heard anyway. That they're just not really dangerous because their fangs are so small. Like if you had like the skin of an infant or something, maybe. But that's not usually the type of encounter. Okay, yeah, I'm not sure. Wait, that's the fear snake. All right. Hello, everybody. Have some interesting conversations about snakes over here. All right. One thing I want to say before we get started is I decided to post the Cryptosporidium participation quiz to Moodle. I have not activated it yet for you, but I'm going to post it right after this class, basically. And so that'll be like a 5 to 10 minute quiz where as soon as you start it, you'll just have a set time amount, answer a few questions for the kind of test that you read it and understood something about it. So that'll be posted, and you'll have basically this week to do it. Maybe I'll put it by the end of Thursday night or something. I'll send an email to everybody just as a reminder as well. So that'll be posted, and that'll be kind of a participation activity for you. I've given the exam situation some more thought, and I decided not to change anything. Sorry to those of you who wanted that. The reason being, today's lecture is not, we're covering a little bit. We're going to finish off the disinfection part, and then it's going to be a bit topical. I'm going to tell you a little bit about my research, some things like that add to disinfection and related topics. And then we're going into the water crisis and then an exam review. So that's like 3 lectures in a row where 2.5, I guess, that we're not really covering course material directly that will be on exams. And I didn't want to push that to an additional one, and I'd rather have some time to go back over the exam number 2 after it without pushing that schedule too tight. So I think this will be the schedule. I think we're slightly ahead of where I was expecting in a way. So worst case scenario, maybe I'll let you off on that day before Thanksgiving break. All right. And in addition, I'll promise to make sure I err on the side of making the exam 2 on the shorter side rather than the longer side, because I know that a lot of you have a second exam that day. So that'll be what I can do for you, given that. All right. So with the disinfection, last time we were talking about straight UV disinfection causing the what we're calling that dimerization between two pieces in the DNA. We discussed that a bit, talked about how that works. Mentioned, I think, the particle interference by we don't want to interfere with the light as it's passing through the water. Of course, the water is going to just absorb some of that energy itself. So we can't design a reactor that just goes like meters and meters of light trying to go through meters and meters of water. We actually want to define the UV reactor in such a way, or build it in such a way where the light's only going a short distance if possible. And so you'll see a lot of reactors that kind of look like a pipe that maybe have that lamp in the middle as a tube, or perhaps on the outside, and it's shining through a few inches of water, and the water's flowing pretty quickly through that and getting dosed that way. The particle situation is another reason why we want to make sure we clean the water pretty well first before we disinfect, because that could shield the microbes quite effectively. Okay, so I mentioned the water itself absorbing the light. Other stuff in the water can also absorb the UV light. This relates to what's called the Beer-Lambert law. If you've done any sort of Gen Chem, you've done this before and may not remember it. If you've done high school chemistry, you've done this before and you may not remember it. This is just simply meaning that the amount of some color absorbing substance, some light absorbing substance in water is proportional to how much light it absorbs. Okay, so the longer you steep your tea, the more of that organic tea materials, those molecules are getting into the water, the darker it becomes, right? It's absorbing more light. So that's just one of our photochemistry laws of photochemistry or whatever. It's just proportional there. And we can know something then about how far the light's going to go if we know something about how much stuff is in there. So we use it all the time to analyze for chemical reagents and things that are in there. And we can also consider how much light that we're dosing is going to make it through, given some information about what's in there. So this little graph is showing the absorbance of light for two different river waters. We've got the Suwannee River natural organic matter. And I don't remember what this one is, a different river water source. So it's the natural organic matter, kind of like tea, right? The stuff that comes out from the leaves, the soil, whatever else, ends up in the river. It's dissolved organics. It's going to absorb light pretty effectively down at low wavelengths. So again, if this is kind of our visible light to the right of here, and right around this range is our germicidal, UVC kind of thing that we're going to use, then what we see is depending on what kind of organic matter and how much organic matter, we're going to have some absorption there, meaning that some of the light will be absorbed by this random stuff in the water that we don't care about. This organic matter is typically not hugely concentrated and would not taste much, would not affect any kind of human health concerns, probably would never even know it's there, right? I did finally clean my water bottle this week, so it doesn't have too much buildup of random organics in it, but there's certainly going to be something in there, right? From, whatever happened to have been in the water. If it had been a while, maybe, whatever just happened to be accumulating there, dust from when I have it open or whatever. Like there's going to be some organic molecules in there. There's just going to be some stuff. And in river water, there's going to be a fair bit of that, and some of it will just make its way through the water treatment plant and into your water bottle. There's just going to be some of it around, and we don't really care about it, but it does absorb some of this light, and so it's going to make our process less efficient in that sense. So we have a specific term for that we call specific UV absorbance, or SUVA. Usually we'll define that, the specific amount of light absorbed at some wavelength. So 254 being the common one for mercury. So that's one way we deal with reactor design and dosing design is, okay, how much light is going to go through, where I would be our intensity, that intensity of light. And we can describe that as we have some initial intensity coming out of our lamp. It's going to pass through some amount of water, and then we're going to have some final amount of intensity afterwards based on how far it went through. That's the other aspect of this Beer-Lambert law. It's a measure of how much light is absorbed over some distance, right? So we can write that as a log of the intensity coming out divided by the intensity going in is equal to this negative parameter here, which is kind of associated with the molar absorbance at some wavelength times that concentration times some distance it's going through. Okay, so you don't need to know too much about that. I'm just kind of showing that that's the feature of it. We've got some amount of stuff, so if we can reduce that organic matter, that will help because it's absorbing some light. Or if we have a whole lot of it, we understand we might have to dose more UV. Okay, so how do we define some sort of a rate equation with ultraviolet light then? And this comes very much back to the concept we covered last time, that Chick-Watson kinetics, where we said amount of chlorine at concentration times time, contact time was important. Here we have some rate at which we're going to kill the bacteria or virus, pathogen, whatever it is, at a given wavelength. So the lambda here is a wavelength, is equal to negative n, so our number concentration to the 1 power first order, times These two parameters, which one of them is a coefficient of specific lethality for light at a given wavelength. And the units here are square meter per joule. Okay, so we have this strange coefficient, but it should remind you of the coefficient of specific lethality that we used when we were talking about the chemical disinfectants, right? A specific rate between chlorine and E. coli, for example, exists. It can inactivate it at a certain with a certain speed. Likewise, at a given wavelength, we could have that same specific coefficient for a given pathogen with a given wavelength. And then this I is the intensity of that wavelength, of light at that wavelength. And so we can express all this as dN dt, create our typical kinetics, where essentially this is very much like negative Kn. I'll say K star. To relate it to the previous thing we did, we said K star is equal to K times C for the chemical disinfectant. Whereas here with the UV, we have, in this case, this pairing of that coefficient of specific lethality and the intensity is pretty much the same thing as saying that's K star. And if we take a look and we combine these two units, they're going to give us per time, right? Because when we do an equation, ultimately this rate equation is a first order decay of N, and it relates by some net coefficient, this observed coefficient of death of this microbe. So we can then say, if we take these units, we have this square meter per joule times this watts per square meter. That would be the units for this guy, right? Well, we know a watt is a joule per second, right? So that gives us simply 1/seconds as a unit. Because the meters squared cancel, the joules cancel, and we're left with 1/second. So that should make sense and be comfortable in the sense that every time we see a first order rate equation, we know that the rate constant, at least once we simplify it down to this like minus K times C or minus K times N, whatever form we're using, at that level, it should be per time, just based on the principles of a first order rate. We have right here some number per volume over time. And so whatever's on the right side of that equation has to end up as some number per volume, which is our number concentration per time, right? And since we already have the N as number per volume, we need the K, or whatever comes in front of that K, to ultimately be per time, right? So that's just coming back to like one of our first lectures. So all that said, the whole business with identifying how much UV do we need ultimately comes back to kind of the same principle. So yes, we can take a look at different organic matter profiles and intensity, light absorption over some distance, and we could do a lot of calculations to see to what extent is the light attenuated and how are we measuring all of that. But at the end of the day, we're dealing with some rate constant, and we derive that. In this case, it's a rate constant that is paired with how intense our light is. And I think I've got an example to just take a look at. We'll talk for a moment about dosage in a second. But ultimately, when you see a UV disinfection problem, just consider this is very likely boiling down to this principle where we have a first order rate constant. Okay, and then maybe you need to convert between the intensity and this coefficient, or maybe some problems will just give you a simple K observed, where we might call this K, we could call that K OBS here. That's the observed rate constant for what's happening. And that's going to account for whatever amount of stuff is happening here. Okay, so if we think about it in terms of like a dosage, first of all, we can say the germicidal intensity is this coefficient times the intensity there. And then a dose, for how much dose have we given a given amount of water, would be an intensity multiplied by time. So just like for chemical disinfectant, it's like the concentration times time. Here we have intensity, which is going to be this watts per square meter times time. Let's just imagine in seconds real quick. That's going to give us joules per square meter, right? Joules being energy, whereas watts is power. So it's power applied over some amount of time gives us a total energy applied to the water. And so another thing you can notice here, just like the contact times time concept, we have the ability to increase time and lower the intensity of our light is the same thing as doing a higher intensity light for a shorter amount of time. Right, and intuitively that should make complete sense, right? If you could do a lot of chlorine for a second or a tiny bit of chlorine for an hour, and it makes no difference, it's going to bleach the same amount, whereas you could do the same with the light intensity. Okay, speaking just a little more about dosage, you could kind of write it up like this, use D as that unit. A few more common expressions, sometimes we'll use millijoules per centimeter squared instead of joules and meters squared. You can do those adjustments. And another word for dosage would be fluence. This means the continued irradiation of a given spot over time. Okay, so a quick example then here for you to take a look at. We'll work through it together in a moment. It says a company is designing a solar-driven portable disinfection system to be used by some military. System is simply comprised of an inlet tube, a pump, a well-mixed chamber, and an outlet tube. Water is pumped continuously into the chamber where it is irradiated with UV light before exiting through the outlet tube and into a collection vessel. The disinfection rate constant for the UV light is 7.80 per second, and the bacterial count of the water must be reduced by 99.9%. And then because this army needs the unit to fit in a backpack, they require that the unit's chamber be no larger than 2 liters. So the question is, how much water will the system produce during 10 hours of sunlight? So take a couple minutes. You should be able to handle this problem. So take a few minutes to test yourself, make sure you can in fact handle the problem. Say if I were to give you this on an exam. Do you want the problem on the exam? I could spice it up for you.
Yeah. No, no. Wait, this is. I don't know. Oh yeah, I need to rewatch all these lectures before I even attempt any exam practice. Yeah, that's fine. That's information. It has to be her assignment, because that's the first second. So results of, yeah. Yeah, because it's the first second. Yeah. Yeah, so now we're seeing, negative algebra.
So hopefully had a good chance to consider the problem. Been slowly writing up a few things here, and I'll go ahead and walk you through it here. So we have a system with some amount of continuous flow into a continuously mixed chamber, or a well-mixed chamber. So flow going in and out, and it's well-mixed inside, really has to be a CSTR, right? So I drew it up something like that. I put a little light and a little mixing thing. We know that there's a 2-liter volume here. And we were also given the design criteria of meeting 99.9% removal. So if we think about how much removal, I'm going to put that as a fraction removed, 0.999 removed, we can say, well, how much is remaining is 1 minus that. And that gives us a convenient way to describe a ratio between what's leaving and what is coming in, right? That's our n over n naught. So that's equal to 0.001 remaining, which should also be the fraction of what's in there coming out divided by what we started with, right? Okay, so that's sort of the problem set up in a way. Then looking back at what the question is really asking us for, it says how much water will the system be able to produce during 10 hours of sunlight? So it's solar driven. So really we need a flow rate to find the amount of water after some time, right? So this is saying how much water, so a volume, right? So we need to take a flow rate times 10 hours to get that answer. So that means we need an equation that can get us Q, so we should think probably mass balance. And we've done mass balances like this. We know this is going to be a first order reaction. In fact, K was given as 7.8 seconds per second. And you notice here, one of the reasons why I give you this is a reminder that what I care about is you being able to take a given problem and understand what you need for it, right? And taking a look at the units is a very important part of that. As I told you a minute ago, ultimately whatever disinfection dose that we're dealing with, at the end of the day, it comes down to some per time unit when we combine it all together. So I could have maybe given you some coefficient of specific lethality and an irradiation dose, implying that you have to mash those two together, multiply them together to get a per time unit. Or more simply, we could just put it as some 7.8. So for example, I could say that there's a coefficient of specific lethality. That wasn't that's lambda. I guess, is this capital lambda? Let's say that is equal to 7.8, and then our intensity is equal to 1. And let me get units here that will match. We could say that'll be square meters per joule, and then it's watts per square meter. So if I were to say this many square meters per joule and 1.0 watts per square meter, that would give you the same exact answer, right? So I could have put these two numbers in the problem instead of giving you the 7.8 per second, because then this times intensity is going to end up, if we have joules and watts in per second, so that combination is going to be equal to 7.8 seconds to the minus 1. So I'm just filling in an example here, right, of what this could have looked like. And my point being that I want you to be able to recognize from a problem, hopefully absent the context of what we were just talking about, because we won't have just been talking about it on the exam, right? And apply it to a problem, because this problem you could have solved as soon as we learned about first order rate equations and CSTRs, right? So this problem we could have done a couple months ago, basically. So let's finish it off, though. Put this aside as just kind of a side note. So we have this mass balance, and we want to solve for Q, which is a little bit uncommon. We're often solving for something else. So I'll just go ahead and solve for Q from here. We could also potentially solve for n over n naught, and then, because we know we need that anyway, and then rearrange for Q to get that in a form of Q. So solve for Q as a function of n over n naught. Either way is fine. It's just going to be making sure we have the algebra correct. So from here, we'll say, I'm just going to go ahead and get the two Q's by themselves and say Q times n naught minus n, factoring out the Q, is going to be equal to, just basically added the VKN to both sides. VKN. So then I'll divide both sides by n naught minus n. So Q equals VKN. Also going to make some space here. This stuff. If anybody wants the explanation of the n over n naught value written somewhere, I'm happy to write it up again. Just let me know. All right, so I'm doing VKN divided by this n naught minus n here. And that's a little messy, but what we can do is divide the top and the bottom by n, and that should simplify it fairly nicely. So Q is going to be equal to V times K divided by n naught over n minus 1. Okay, so now we have just about the form we need. In fact, we could just leave it like that and say, well, if n over n naught is 0.001, then n naught over n should be 1,000, right? Just 1 over that. So that means our flow rate is going to be equal to the volume of the chamber times that constant divided by 999. And here we can grab calculator. And say that volume is 2 liters times the 7.8. 7.8, divide that by 999. So this is going to be, we have liters and per seconds there. So this should be liters per second as a flow rate. So 0.0156 liters per second. And so then we need to multiply that by the 10 hours. And we'll just go ahead and multiply the hours by 3,600 seconds per hour. And that should give us our answer. I'm adding in the 10 hours here to get our final volume. 561 is here. So times 10. Yep. Depending on how you round it, I went ahead and kept all the digits there. So about 562 liters in 10 hours. Okay. Does that make sense? Any questions or issues? So do you get mad at me or yourself if I give you a question that's simpler than you thought it was and you get it wrong because it was simpler than you thought it was? A little bit of both.
I was thinking myself the wrong way with the whole. We came up with a concept that you had boxed away, but not necessarily that it was exactly K.
Okay. Yeah. So just a good practice would always be to write out the units, right? Like and even before you're solving everything, you know that in some way this is a dNdt type of a form. So you can check to make sure that whatever units you're about to plug into your rate equation are the correct units in that manner, right? That should hopefully help that situation. All right, so that's it for the directly disinfection stuff. From here, I'll just tell you a little bit about some research that we've got going on, making use of some of these principles. And this will be a way for me to tell you a little bit about advanced oxidation processes as well. So we mentioned advanced oxidation when I introduced the chemical disinfectants and talked through the different disinfection strategies. And then I mentioned kind of ozone plus UV can be an effective way to destroy stuff. And certainly it would destroy a lot of microorganisms. But sometimes we do that just primarily to destroy like the pharmaceuticals or whatever else other chemicals we might be concerned about in the water, not just the viruses and bacteria. Okay, so specifically what I want to talk about is the use of LEDs. So we have LEDs kind of everywhere now. Even the lights on in here are very likely LEDs that are arranged in a strip to kind of meet the similar form factors we're used to seeing with the fluorescent bulbs. And so recently we've been able to use our kind of modern technologies to develop LEDs that shine in the ultraviolet spectrum. And that's pretty nice because as we see, indoor lighting has transformed. They're less likely to burn out, so they have better lifetimes. They don't need the whole ballast system, so you don't have that secondary system that could also burn out, so to speak. So they don't require mercury vapor hanging around in indoor spaces to function, right? So there's some benefits there. They're a lot more robust. You wouldn't want to put a fluorescent lamp on the side of your handheld device so that you can shine a light sometimes, because what happens if you accidentally drop it, right? And then it breaks. But my LED, I'm not worried about that. You guys are like, I'm worried about, I may have, dropped that on here on accident and broken that, right? I think I missed. Everybody else is just sort of startled. Why would you drop your phone, right? But it's designed that a little 1 foot drop like that is not going to be a big deal. And I wouldn't have that confidence if there was a little, mercury vapor filled glass tube sitting right there, right? So there's some inherent advantages on that side. But there's also some neat things we can do because it's giving us more color options or more wavelength options. Just like the clothing that we wear has different colors because of the light that's being absorbed, it doesn't take a huge shift in the wavelength to create a different color to our visual experience. And that means that molecules are acting differently based on small differences in the wavelength of light that's going by. And so in a similar manner, some of the research we've been doing is taking a look at, can we make use of that shift in wavelength and some of these other properties about LEDs to, create or make use of more advanced ultraviolet-based technologies. So that's on the disinfection side and the advanced oxidation side. So we'll go through a couple examples about that. So case in point here, just kind of making that point, dropping my phone. Some power efficiency expected as LEDs become more efficient. I think the indoor lighting, we're at the threshold where it is definitely more energetic to use an LED compared to just about any other source. And you could call that like the wall plug efficiency. Like you plug it into the wall, you get some amount of lumens or intensity of light, watts per square meter, for example, and you could compare that to other lamps. The UV LEDs are not there yet, but I don't see why they won't approach that, if not get there, given that we've had that same success in our other systems. Cost, as well as they become produced more, that'll come down as well. Okay, there's the other aspect that it's just kind of fun in a sense. But so if you've ever seen like the little the light shows with Christmas lights, you can do that because these are LEDs and you can instantly turn them on and off. So while that's a whole lot of fun to look at and everything, the other thing we might be able to do is make use of the fact that you can basically instantly go on and off meaning you can adapt your dosing very carefully and perhaps even make use of some clever tricks with the advanced oxidation side of things, where we create these very highly reactive radicals that will basically, once we create them, they'll react with anything almost instantly. And so one of our ideas or hypotheses that we're working towards is seeing, well, what happens if we pulse the light kind of on some similar scale of how quickly these oxidants are reacting? Can we perhaps get them to live a little bit longer because we're not blasting them with more and more light? Or perhaps can we let just a few microseconds of time pass by before blasting another pulse of light through so that the water can mix a little better? Can we get some advantages from practices like that? There's also simply the benefit from not having to have a long restart time if, let's say, the power goes off and you have to switch to a backup generator. Is one key advantage. Or if you're just wanting to install an LED onto a small bottle or something, you don't have to wait for the lamp to warm up 20 minutes before you're sure that you're getting enough intensity. All right, so there's all sorts of advantages with that. The fact that they can be instantly on and off.
So how does
What's that?
So how does UV light kill germs? Because
Okay, that's a good question. And I'm just going to flip back to my slides from last time because we did talk about that a little bit. But now that it's interesting, it's worth talking about again, right? Okay, so essentially, UV light doesn't necessarily kill germs so much as it causes them not to be able to replicate, typically. And so the same reason we're concerned about too much sunlight could give us some cancer risk. Well, it's because it's disrupting things in the DNA. And that can be one of two mechanisms, one being direct UV absorption by, if I can do this and I can see. So we'd have direct UV absorption by the molecules in the DNA itself, causing two of them to react together right here is where we're showing that. And so then these two thymine groups then fuse together as if we put like super glue between them. Now they are one chemical instead of two, or one molecule instead of two. And then the enzymes that zip and unzip the DNA can't go past that spot. So they get stuck, and they can't replicate. So even if it can live for a little while, it's not going to be able to reproduce itself because the DNA is not able to multiply. It'll probably, if you do this in enough spots, then the essential DNA required to function, for the cell to function, will also give out, and then they just will die shortly thereafter for whatever metabolism and stuff.
So does sunscreen work like in a completely different way than that?
So what sunscreen does, a great question. Sunscreen, what it will do is absorb the light before it can go too far into your skin. So sunscreen, essentially, if we take a look at, I should really get a solar spectrum in here. Maybe I'll pull a figure up in a moment. If the sunlight goes something like this, where we just get a little bit of this, what we call UVB light, and then it goes on, sunscreen is going to be really effective at absorbing a lot of this light. Well, definitely the UVB as well. So if you use plenty of sunscreen, then basically none of this UV will get there. And if you use so much that your skin looks white, you're absorbing some of the visible light too, right? It's just, or scattering it. It's like that white powder, because it's generally filled with TiO2, titanium dioxide, and zinc oxide, ZnO2. Those just happen to absorb UV light very effectively, but not so much visible light. So if they absorbed visible light, then it would probably color your skin in addition to making it colored to the UV range, right? So it's absorbing all that UV light, but we can't see the UV light, so it just looks like your skin is your skin when you put sunscreen on. So the goal of sunscreen then is to grab that light before it can get really far into your skin and affect anything that's doing replication. I think I mentioned last time that random acts of oxidation. That's another way you could kill the germs, or your skin could be damaged based on chemicals, just different molecules in your cells becoming excited and then easier to react with oxygen, or maybe sensitizing some reactive oxygen themselves, rather than that direct UV damage. But either case, most of the time when we're using UV, we're doing that germicidal specifically. Sometimes we'll use like a photocatalyst or something, and that'll generate those random acts of oxidation much more frequently.
So what's the best way to not get sunburned?
Best way to not get sunburned is to, well, I mean, it's a good question. So if you have a way to reflect or scatter the light before it hits you, so if you're in the shade, or some way to absorb it. Either way is fine, right? You could stay indoors all day, no fun, or you could wear long sleeves. Might not be that worthwhile unless you have really nice clothing for it and a good breeze or something. So perhaps just sunscreen, and then the other thing about how the sun interacts with our skin, pigments are essentially antioxidants. So these random acts of oxidation, well, when your skin senses that you've been exposed a lot, then it will start creating more pigment, right? I could show you a pretty good farmer's tan if I wanted to, right? Because some of my skin has received a lot of sun, and so it starts producing some pigments, and so that pigment it'll absorb the sunlight, so that other molecules further in don't, and they also tend to act as antioxidants, meaning they will be the first ones to end up reacting with these random acts of oxidation occurrences. So they're going to scavenge the oxidation that's going on. So in some cases, a mild sunburn is probably not a huge risk, as I understand it. I mean, I'm not a medical expert, but I think mild sunburns are not a huge deal, but what you want to avoid is like the really severe ones. That means you've taken a lot of damage and that potentially, or much higher potential for permanent stuff, whereas maybe a mild one just sort of triggers you into producing more pigments, right? And of course, everybody's different, skin colors, everything is going to have some impact on the degree and extent of all that, how much it matters and all that. Okay. So, coming back to then what happens when we change the color of UV light that we're using to disinfect. Maybe we can do some smart disinfection simply by targeting a different wavelength that is making just as good, if not better, use of that germicidal curve to capture those DNA excitations to damage them, and have less issue of that dissolved organic matter I was talking about. We saw a couple of pictures of that. So less SUVA here. Let's see, why is it not? Something's happening weird. What's that?
I was going to ask why the curve for the LED was dashed on the left side. Is that just like frequencies that get hit? Well, when you get to it.
Okay, so apparently I was making marks and it just didn't look like it was. Okay. Okay, so you were asking why the dashed lines?
Yes.
Oh, man.
Why is there do this?
I can't erase it. Dashed lines was just because. It was not really a purpose. So I was mentioning earlier that the dissolved organic matter that I've now thoroughly highlighted, trying to get my pen to work. If we can absorb less of that light, we can cause less of the light to be wasted based on the presence of that dissolved organic matter, we can get some tangible benefit in terms of efficiency. So that's one thing, if not anything else. There's some other questions we had about if we do make this shift, well, what happens if microorganisms are not damaged in the same manner? Does it have different implications for how well the technology will work? And specifically, we got curious about this because we learned that some microbes can actually repair themselves after DNA damage from ultraviolet light. And they actually have this cool machinery, this enzyme called photolase, that's activated by light. So basically when the bacteria senses there's light happening, it powers this little enzyme. So it's like a photovoltaic enzyme in a way to go through the cell and repair these thymine dimerizations and some similar ones. So this enzyme will just be going throughout the cell trying to repair itself whenever it's activated by light. Now, it's not perfectly effective at it, but if you do a disinfection experiment and then put that organism or that water that has these damaged organisms under some light, especially kind of the blue or slightly ultraviolet, then this enzyme will be activated and it will be repairing. So we had a question about, okay, well, does the initial damage in the first place have some impact on this repair mechanism? And the repair mechanism was, just as a side note, people found this and won the Nobel Prize for discovering it in some sense because they did just that. They did some sort of disinfection experiment and then they noticed maybe they accidentally left the lab light on or off or whatever. And one case was different. So they were like, hey, it looks like, they're somehow recovering under this one condition. And then the researchers went on to say, oh, maybe we can create a new skin therapeutic, right? So we have this sunburn. Maybe we can harvest this enzyme or whatever it's causing the repair so that we can put it in sunscreen. And then this, whatever it is, can help our own skin repair. It turns out human cells don't have this photolase enzyme. And so the researchers were thinking, well, we've done this with penicillin. We've caused a bacteria to produce something that was very useful for us. It created a pharmaceutical for us, antibiotic, or I guess it was the yeast or something that was producing it. So we can do that in some cases. So they tried to do it and ultimately discovered that each bacteria cell has like 3 or 4 of these enzymes in it at most. So it's very, very small amount, which is why it took so long for them to discover it. But it's really a kind of a neat thing that it's a light activated. So if you take UV and cause that dimerization, it's a little upfront picture of it. Whereas normally there's no bonds here. That's the normal way of things. They're attached through the DNA backbone or whatever it is. If UV causes those to bond together, then this enzyme reverses that reaction and makes what would otherwise be an irreversible reaction actually reversible. So it's kind of a neat thing that exists, but it's not so good if you want to disinfect water and keep it that way, right? Especially if you're disinfecting wastewater, discharging it out into a river, and then it gets a bunch of sunlight, some of these organisms can repair. So we recently published the following work here on that specific matter. So these are intensity spectra. You see this microwatts per centimeter squared, pretty similar to what we were talking about earlier. And these are the ones we actually used in our lab. So we had a UV 254. This is a mercury lamp, and this guy's an LED. And so we checked on, first of all, how well did they kill the bacteria. Here we're using E. coli. And up top, I have fluence here. And again, that's basically time, except we also multiply it by intensity. So this is a way even if we had different intensities between the two lights, which we did, we can normalize them so that we can compare them directly. So that was pretty handy. And what we find is the LED is working pretty well. LED here is in green versus the mercury. And it's a little different, and perhaps maybe we can adjust that metric a little better than we did. But it's similar. The E. coli are dying. There's a little bit of a lag at first, which is, in practice, is kind of common. They're not immediately going at this first order destruction kinetic sort of thing. A little bit of UV light they can handle and probably repair themselves from, and then they start dying off pretty rapidly. So, by the way, this is like for a not a particularly strong light. It would probably be like staring at the LED of a flashlight or something. Something around that intensity for practical purposes. And then in terms of the time, this was like 4 to 5 minutes, I think. So just a little bit of bacteria in a petri dish in the water underneath a lamp that's shining on it with this UV light, giving, a few minutes later, we've killed almost all of it, just as kind of a tangible example. Okay, so then we checked how well are they recovering, how well can they repair themselves. First we did dark, so there's some dark repair possible, especially if we give them a bunch of nutrients. So some of them grew back a bit, somewhat expected. And then we gave them some UV light on that backside, but this is UVA, so kind of like blue, violet, slightly ultraviolet light, or some visible light here, just these different spectra, just to kind of see how well is this photolase enzyme working, and can we differentiate between the LED and the mercury lamps to begin with. So we continued, we got a bunch of data from that. I'm going to kind of gloss over it. And ultimately what we were looking to do was to use this particular model here to learn something about how the two different lamps, two different wavelengths, the colors, are going to affect the outcome. And so what we see is we have the blue, this was the mercury lamp, versus the LED in the green, were actually quite different in terms of what percentage of them survived over time given some repair conditions. So it looks like maybe we get an advantage using this LED system where they're not repairing themselves as much. So that was kind of one of our conclusions. This equation over here is kind of interesting. If we think about it, what we're doing here is we're putting together several different reaction rates into a mass balance. So guys, I know you love all the mass balances here. This one's pretty tricky though, because part of it has to do with there's only a percentage of them that were damaged in the first place, right? So if we're looking at, we need a rate of repair. So R repair, we might have some R of bacteria just simply growing as possible over, because this is several hours, right? And then we also have a stressor of giving them this slightly ultraviolet light, that in the realm of random acts of oxidation, right? So R of death. So we have these different rates, but the repair can only happen on the portion that were damaged in the first place. So the rate equation, once it's all derived and everything, which fortunately somebody else did for us, published previously, was based on some fraction that had only the fraction that had been damaged instead of the total. So anyway, it's just more rate kinetics applied so that hopefully we could predict, again, what happens if we disinfect wastewater and send it out to a river, or disinfect water to be sent down the pipes, and then my bottle sits in the light in the room, right? Is this a concern? Well, that's one of the reasons why we add that residual chlorine, even if we're using UV dosing as our primary disinfectant. So we don't want regrowth later in my bottle. Okay, talked about that stuff. All right, so then we could talk for a minute about advanced oxidation processes. In particular, one of the things we've been interested in is using chlorine itself as an advanced oxidant instead of a conventional oxidant disinfectant. And the reason we are thinking about chlorine is because conventionally we have something like UV 254 right here from the mercury lamp being able to excite, and this is by the way, a graph of absorbance, so light absorbance by the two different chlorine species. If we're exciting it with a mercury lamp, it's not doing so great. It's just a little bit of absorbance comparatively to if we were able to move our intensity, let's say, to near 300, we could get a much better absorption, right? Up here is way higher than there, but that also means we need to use OCl minus. So this is something we've been exploring because the LED gives us that opportunity to shift our intensity effectively right into this realm of using OCl minus instead of the HOCl. So got a bit of data on that. Use this advanced chlorine oxidation. Oh, well, here you go. I showed the actual data there. And when we excite chlorine, there's a whole lot of chemical reactions that can follow if we are doing this photolysis. So if we split apart the chlorine molecule, then we could create chlorine radicals. So this, the HV here is that's a UV light or UV photon. So if we react HOCl with light, we can get a chlorine radical and a hydroxyl radical. We could split the hypochlorite and get a oxygen anion radical, so O dot minus. So oxygen doesn't like being by itself. It'll react with something pretty quick. And a chloride radical. So all of these radicals and all sorts of sub-reactions are possible and probable during a reaction like this. And each one of these could then go and kill a microbe or react with, let's say, some heroin that's in your wastewater or something, right? So sometimes we just want to try to destroy anything at all. Maybe it's a pesticide, maybe pharmaceutical, whatever it is. Sometimes we just want to try to destroy everything, especially if we have some sort of reuse application in mind for the water. Maybe we want to make use of the wastewater and the nutrients that are in it to irrigate some plants or something, but we want to do it in a manner where we're not accidentally exposing whatever comes next to hazardous compounds, right? We don't want to just take raw waste water and send it into a farmland, for example. So that's kind of the purpose of the advanced oxidation. So with all of this, the types of reactions we get are wavelength dependent and pH dependent. So there's a whole lot to explore, and we've gathered some data on that. And it turns out that we can actually end up getting some ozone out of the system based on some of these reactions that ultimately create ozone right here. Because some of the reactions will produce ozone that stays a little longer. Yes, it can absorb the UV light as well, but it's at that range, it's not doing it super well. So it'll last a little bit longer, which then can perhaps do a better job destroying some chemicals. So we've got a lot of data, and the point being is we can compare, just like we've done in class using our C over C naught stuff versus time, and plot our data like you see and get some K value. This is literally what we do to analyze the data and see, okay, well, which case performed better? So we're doing a lot of this rate and kinetic analyses, and you see all this data up here for specifically that. All right, so we did a bit more. I'm going to gloss over this a little bit. Essentially, what we were looking at is a few specific pharmaceuticals, whether it's acetaminophen, carbamazepine, which is a antibacterial, and testing for different radicals, how well they worked. So we see all these different plots of, hey, this one in the green worked pretty well, blue not so much. So here, for example, we're showing that at pH 8, where we're going to get that OCl minus dominating, that worked out pretty well. And we got a lot of probably what's probably ozone, unless we removed all the oxygen from the water, and then we don't have it. That's blue. Okay. So then we tried some pulsing experiments, and essentially these are showing a dark line across where this was the value we got if we just didn't pulse it, we just kept it on the whole time. That was the value. So in some cases, when we pulse it, we had some improvement, which is pretty neat. And this is the case at pH 3. We see pH 8, we have even better. And it kind of depended on how quickly we were pulsing and what kind of what percentage of the time on or off. So we had some maybe 10% on, 90% off, or vice versa, or 50-50. So we tried a whole lot of different scenarios, got some interesting things. We need to get this out for publication soon. So anyway, that's quite a lot. And looking forward, we could potentially do even more and even more complicated systems if we can get our heads wrapped around it. With chloramines, I mentioned this the other day, but when we react chlorine with ammonia, we get these chloramines, and they could also be potential advanced oxidant candidates. So that's another thing we're kind of looking into. Okay, so I think I already told you about this. We made a little UV LED for water bottle. And some of these small scale systems are definitely one of the project designs that we're looking at. We're also recently started working on a project with the EPA, with Dr. Aaron Bivens, it's a new hire in the environmental group. We're working to build an LED-based reactor to treat wastewater from these at-home septic systems, but not truly septic in terms of like sending it out to a septic drain field, but like a aerated treatment unit that discharges then to a ditch. Apparently there's quite a bit of those in Louisiana, which is quite interesting to me from a environmental and regulatory standpoint. So we're trying to design some LED systems while also tracking to see if we can see if some of the bacteria in the rivers can be sourced back to these practices. Okay, so a lot of people have been involved with these projects, and if you guys have any more questions, happy to entertain them. All right, so that's all for today. I will post that quiz to Moodle and send you a note about that. And I'll see you guys on Thursday.